Hey Eric, what's up, man?
Hey, not much, man. How are you?
Good, good. How you been?
It's been a while.
Yeah, dude. Yeah, you. How does? I'm trying to get on the freaking the Pangburn debate tour circuit myself, man.
Really?
Sure. Yeah,
Nice.
yeah, dude. That'd be amazing.
You should, man. You definitely should.
What are the time estimates? I mean, it really is. It's hard to say, guys, because it's so bad right now that anything. It's like you're smoking a pack a day, and you're like, so how long until I need to change? And it's like, well, I mean, the risks are only increasing. So it's one of those things where here's 2050, right? Here's where we are. And so we're basically, we are on the pace where we are on the high risk path based on the IPCC reports of 15, 20 years ago. So like if we continue on that path, we're only going to be on that high risk. So, we need to start mediating at least, and the numbers, it's only easier now. So, and this is why I was such a big fan of the Inflation Reduction Act, of the infrastructure bill. These are like huge investments that the United States made in order to start mitigating some of this stuff for the first time. For the first time, we are actually investing in the technologies and the research and the infrastructure to actually get us on these paths. But it was ripped from us. Our future was stolen from us for this. And that's what's so frustrating about it. And it's like, it was literally just stolen for tax cuts for billionaires. It wasn't even used for anything that was, good or it was just, it's insane.
Yeah, man. It's pretty bad.
Yeah.
Have you um have you uh have you at all have looked into like where we are in terms of attaining nuclear? Have you heard anything about fusion?
I have a friend that works at UCSD, and he said that there's like amazing progress right now that they're going into. Um,
I mean,
Here
I'm
we
pretty
go.
sure it's expensive to invest in that technology,
Here we go.
but I think
UCSD
it's
will
necessary.
lead a research team. Whoops. Here we go. 1 second. Yeah, dude. I think that we are. You know, I think that there are people that are working for it. I think we, at our detriment, kind of stir in hopelessness when there is actual research going on that is trying to actually make things a reality, and like
Yeah.
stuff like this is true. It's just we don't know about it, right, guys? I mean, it's not anything that's malicious. Again, it's just like incompetence of our media to understand what's actually happening. Oh, really? Dr. O knows a lot about this program and the nuclear programs. Oh, cool, Scott. Yeah, 4 million in new funding brings together researchers from 4 UC campuses and 2 national labs to solve fusion energy grand challenges. The University of California, San Diego, my alma mater, has been selected to lead a new multi-institutional effort aimed at solving materials, fuels, and diagnostic and workforce challenges required to make clean, affordable fusion energy at a commercial reality. $4 million grant from the UC National Labs Fees Research Program. So again, guys, these are the programs that Trump stymied and he stopped. By the way, this is what we're talking about.
Right.
Here we go. Quote: Fusion energy is one of the boldest frontiers in science and is one of the most promising pathways to clean, sustainable power. California's extensive network is ideally positioned to solve the scientific challenges of harnessing, capturing, and delivering fusion energy, as well as the complex economic policy and public components. UC San Diego is proud to lead a partnership that will advance the science, the technology, and equip the skilled workplace that will make it a reality. And this is what we're talking about, guys. Public programs. What billionaire is doing this? What billionaire is making a non-for-profit organization that is trying to spearhead and create research programs in order to solve some of these problems? Do you think that your money, that four
Isn't
million dollars,
France?
it's only $4 million? It's like, oh, go ahead, sorry, bro.
No, it's all right. I heard France, they power their grid with 60% of it is powered by nuclear, right? I don't know
Hmm.
if you know anything about that.
Oh yeah, Dave Marvin in chat. Thank you. Thank you for saying that, Dave. I'm glad you found me from in time, man. ITER, the international project, is the biggest fusion project in the world in France. Cool. Let's look. Let's see. ITER, France, fusion. I had heard about this. The International Nuclear Fusion Research. Is it ITER? Also meaning the way or the path in Latin, is a international fusion research and engineering project designed to demonstrate the feasibility of fusion power. The facility is under construction near the Cadrants Research Center in southern France. ITER has been under construction since 2013 and is expected to achieve first plasma in 2033 and 2034. Is that a good outline? 6 years, is that a good? I wonder if that's a good time frame. At which point it'll be the world's largest fusion reactor with plasma volume about 6 times that of Japan's, the previous largest tokamak. What are these words? What are these words, guys?
Oh, so they're also investing in fusion out there then. No, but
Yeah.
currently they have a lot of fission energy, I think.
Yeah,
Like currently,
that's way cool.
yeah, they've been working on that for the last couple of decades.
That's amazing. Here's a small scale model
it's
of
where-
the ITER. Wow.
Yeah, it looks cool as fuck.
That's very cool. What? It's massive. Let's see. Let's see what the Japan. Okay, so this is ITER in France. Oh wow, yeah, Ronald Reagan. Dude, I mean, this is it, guys. I mean, isn't that amazing? I mean, we're talking about. This is what I love about science, of where it's like a international. We're doing things that are bigger than any individual, right? Or any individual state. We're coming together and actually trying to solve problems. Wow, this thing is gigantic.
Yeah.
Wow. That's so cool, man. Whoa. I love it.
So this is ITER right there, right?
Yeah, the drawing of the integrated systems. So it's just one? It's just one massive one of these?
Well, I think this is what they're investing currently, but you should look into what infrastructure is already there right now, because I think they're on the I'm pretty sure they're at the forefront of nuclear right now. France.
Yeah, for sure. Seems like it. That's amazing. I want to learn more
We're
about
playing catch up right now.
Yeah, for sure. Seems like. Wow. What are these cross section of the part of the planned the fusion reactor vessel? What is in the vacuum vessel? Okay, it's a vacuum. Okay, so the vacuum.
Oh, go ahead. Sorry.
Is it? Go ahead. Are you gonna answer Hazel's question?
Yeah,
I have no idea.
Yeah, CERN. I don't think it has anything to do with CERN, right? Because CERN is what is CERN about?
That's the particle collider.
Right. That's right. But they research. What is it? Nanoparticles, right?
They're doing like even smaller than nano. Yeah,
Parts?
It's like they're like the smallest particles they can and then as they blast into one another, they're like tearing into. They're losing things, and it's like losing parts of part of it. Thank you, Ness. Yes, I agree. Europe is doing cool things. Thank you. Dave from YouTube chat. It's like a giant magnet, like a donut. The plasmid sits inside the donut. Wow, so it is filled. So it's not just like a vacuum. It's actually filled with plasma. This thing would be filled with stuff. And then held in place by electromagnets because it's the temperature of the sun.
Really?
Wow. Holy. Wow. So it'd be filled with stuff? Dude, I want to maybe we can watch a video about this. It'd be cool. Let's see.
Plasma meaning like super hot particles,
that's
right?
the fourth phase of matter.
right?
ITER.
Where where mass becomes like liquidy, I guess, or something like that.
Yeah,
It acts
exactly.
kind of like liquid.
Okay, so this is wow. Well, this is cool. It just got new video just dropped, guys. Okay, so this is cool. This just dropped 15 hours ago from ITER.
On November 24, 2025, Sector Module Number 5, the third module of the vacuum vessel and the very first built in Europe, was ready to be installed into the tokamak pit. But such an operation doesn't begin with a lift. Its preparations started days earlier.
The maintenance
That's
team
huge.
and the cranes operation team, we do the pre-checks. So basically what we do is check greasings, we check alignments, we check sensors, we check ropes. We discharge some variators, some variable speed drives in the cranes. It deserves to do in order to eliminate electromagnetic disturbance.
Wow, that's amazing. I mean, are they like learning what to do on this stuff from like small scale reactors, and then they're creating. I mean, this is like just the amount of steps that you have to take. You know what I mean? You don't want to screw anything up. Welcome up, dude. How's it going, drone?
Yeah, you're right, bro. Yeah, I just really want to discuss this because I'm an
Yeah.
engineer and a BFIS.
Sure.
I'm a master's engineer in BFIS. I just want to say the problem is we've got with the prompt is confining the plasma. We can't. It is like millions of degrees, and if a few particles get out, it's going to blow the fucking reactor out, and basically it's fucked.
So that's what this is,
So-
right? So that's what these like vessels here. That's what this is. So this is the actual reactor vessel, and these are all magnets on
So
the
it's
side
both-
here.
Yeah, so it's trying to magnetically confine it in a toroidal magnetic field that rotates, and well, not exactly rotates, but it's in a toroidal. And if one of them gets out at 2 million degrees, you're done. So that's
wow.
why I've only done it. I think the Chinese have done it for 6 seconds. I think we've done it for 3.
Wow.
We are making a magnetic confinement at the moment, which will confine it more. If you can get the video up, right? Get the video up of that 6 second fusion reaction.
Sure. Okay, let's watch that after this. Okay, we'll watch that after this for sure.
Then we do what we call the RASRAX. This is an acronym, but it's a calibration of the hooks. So basically, we align all the sensors monitoring the positioning of the hooks and the cranes on the same basis, calibration. So you can see behind me at the end of the crane hall, so the 2 cranes with the 4 hooks, so below the girders. So these 4 hooks will take this spreader beam, the dual crane heavy lifting beam, at each corner. And then after, at the center of this spreader beam, will be attached the rest of the rigging to be mounted on the sector module 5, to be able to lift on Monday the sector module 5 to the pit.
Dang, so they haven't even started putting this together. They're like still
No, we have. But it's ITER did it less. But if you put up fusion reactor video, it'll come straight up.
Okay.
Do they use hydrogen for fusion, right, instead of uranium or thorium?
Well, it's an ion of hydrogen, but yes.
Right, because I heard that the thing about fission is that the radioactivity of it is because we have to use those unstable elements, whereas fusion, you could use stable elements like hydrogen or helium, but I guess hydrogen would be
Right.
the one.
Okay. Right. Okay. So yes, you are right. This is the key. Okay. So the key. Sorry, go on, bro. Just finish your plane, and then I'll finish mine.
So I guess the challenge is what you're saying is that the challenge is to harness the the energy that comes from it, meaning that it gets really, really hot, is what you're saying.
Right, okay, so it's E equals mc squared. So you've essentially got a sun inside that donut. There we
No
go.
way.
Look,
That's
there's the
so
video.
cool. No way.
Look. Put it up again.
Oh, whoa! We went to the top there. It's like going
Do a slow
around.
motion.
Oh yeah,
Do
that's
it
a good
slow
idea.
motion.
Yeah, that's a good idea.
Yeah.
Playback speed.
25.
Right, so that is now. So
Whoa.
on that screenshot, that is magnetically confined, so it doesn't actually physically touch the sides. It is currently about 5 million degrees.
Wow.
So if that touches the sides
Whoa.
of that,
It goes to the top. It went right to the top.
And I'm not talking 5 million F. I'm talking 5 million C.
Wow.
Jeez.
I could convert that into Kelvin if you want me to, but so it's whipping round that fucking donut, like.
Yeah, just like
this
it's crazy. So
this is all harness.
So this is this, guys. So this right here. So we have down at the bottom here this cross section of the fusion reaction vessel. So it's down here at the bottom of the thing, and then it starts here, and then it lost itself, and then wound up over here at the top. So I guess that's when they stopped it off. But Dave is saying that if you turn off the magnets, it's really safe because you can just dissipate it in milliseconds. That's what he was saying.
Yeah, it will stop. Yeah, it stops straight away.
Gotcha.
But the problem is what we do is we use the whole, like, we call it a tokamak. So we use like the whole donut at first, and then bring the magnetic field in and drag it straight down and speed it up, so we get more and more and more energy. But then we get more and more heat, and then if that comes out of the constrainment. We're in it's gonna go Chernobyl. Like, do you get me? Like,
dang. So this is the 2D of the polyidal plane. So this is all the magnets, the magnetic fields on the left hand side here.
Yeah, that's it. Yeah, that's it.
Interesting, and then the cross section of it on the right.
Yeah.
So the fact that it was at the bottom is actually, it's like outside of that. So okay, interesting. So it's using yes, Rapture. So that's interesting. So it's using the speed and the magnetic fields in order to spin it up, and then it's pushing it down to the bottom here where it has less of the field.
No, it has more velocity. It has more velocity, so it has more kinetic energy. We use that. But the problem is, don't make it touch the bottom, because if it touches any side, but then when we speed it up, and the energy levels get up and up and up and up, we have to up the magnetic field to make sure it don't hit the bottom. Because if it hits the bottom, it's gonna go pop pop. It's gonna go pew pew.
Dang. So this is Japan's. right now, I guess. This is the DIIID vessel on maintenance. Dang. It's so like, this is in San Diego. This is the D3D that's been by General Atomics in San Diego. Wow, I didn't realize that.
Yeah, but if we can work this out, right? Photovoltaic cells, like solar panels, like wind turbines, coal power fire stations, everything is just gone. We have got unlimited energy, and we can make it out of essentially like an ion of hydrogen.
Wow. Right? Dave is saying it's pushing from all sides and creates a donut of plasma. At that point, the elements are fusing and creating immense amounts of energy. Interesting.
Right. Okay. So I want to say, right. Okay. Just real quick. Well, there we go. Well, that's a laser one. We don't always use lasers. There's different methods of doing it.
Okay.
But can you imagine if we just had the free, like, bang water in it, there's no radiation, and we've got free energy?
Yeah.
Like, it'd be brilliant. But it's contained, we're basically containing a sun inside this reactor.
It is
So,
wild.
yeah, it's wild. It's.
I mean, that's so cool. I mean, it's crazy because it's always been like this mythical thing that I had heard about for so long, but then it just seems like we've made a bunch of breakthroughs recently. I didn't really understand it until now.
Well, the reason why we shut it down, the reason why we shut them down so quick is because it's like, oh shit, is someone going to get out of the confinement? So we just shut the thing down real quick because, like, we don't want, like, the prototype to fuck up.
Yeah. So this is the current biggest one. It's still pretty big. It's pretty giant.
Bro,
Wow.
if that thing blows up, this is why we always shut it down. Because if that thing fucking goes and you've got basically a sun inside of it.
I know that's how the latest into the universe with the Spider-Man movie. That's how it all started. I saw it, the alternative reality Spider-Man into the Spider-Verse movie.
Yeah, I'm telling you right now, bro, right? As an engineer, if I saw any of the data getting out of pop, I would immediately go, fucking big red button. Shut the fucker down.
For sure.
Well, you're not going to get dragged into HR, are you, and explain to your engineer above you and go, why did this fucking reactor blow up and you might be dead?
Yeah, exactly. You might not have to worry about it.
Only my wife. Like, you just shut the fucker down, don't you? So.
The criticisms. Yeah, it seems to be some I don't really understand. It's like inside baseball of how it's happening, the cost of it, the impact of it. I mean, the cost and stuff, like the whole point of these things is that you're doing things that are bigger than profit can make. That's the whole reason. I mean, these are projects that aren't profitable, but science and technology kind of needs that at the beginning. So it is, billions and billions of dollars for sure. I don't know if that's wasted though, necessarily.
Yeah, real quick. That's perpetual. So yes, it does cost you a lot of energy and joules to get there. Okay,
Yeah.
But then once you've got there, it's perpetual. It will just keep running. It never stops until you shut it down.
Oh, really?
So
wow.
Once it's going, it's free. There is no energy requirements. All you have to do is bang into deuterium or He3, and basically that's where we're at. But it's always 10 years away. We can't. We're trying to contain a sun inside a small donut, which is a tokamak. Like, you're trying to put the sun into a fucking donut. Like, can you imagine, like, I'm an engineer and I'm a physicist, okay? But trying to get a sun and get plasma, the fourth state of matter, into that and keep it stable and keep it creating energy, and then having to work out how you're going to make steam from that to drive a generator.
Yeah, I mean, that's a good point. I mean, I feel like they chose the wrong shape. If you wanted to contain a sun, you don't do a donut. You contain a sun by nailing him to the cross. That's what you do. That's sorry. Sorry.
Yeah,
I'm sorry. Sorry, that was for you, Lighty's Life. That is for you. That's for you. There you go. I'm sorry.
Yeah, but there's a few. You need to rotate it because you need to get more energy into it. And you use the rotation and the angular momentum to increase the energy, which gets you there. But then you've got to work out how you're going to get that into a steam turbine and generate heat. So you're going to need exchangers. You're going to need this. Like what material is actually going to take 1,000,000 degrees?
Yeah. How do they like? What is the scaling up like when something that's this big? Like, how do they scale it with like different materials, different? You know what I mean? Like, what's been the road to here? Like, it must be because I'm assuming that the argument is like we need enough energy in order to get it to this critical state, and if we don't have that at that critical state, like what can we learn? So I guess are they trying different like substrates or different stuff in the chamber, or you know what I mean? Like how?
Yeah, we're on about going to titanium. There is another metal I can't remember at the moment because I'm on quite a lot of meds because I've got cancer at the moment. But I don't want to get into that.
Oh, sorry, brother.
No. I've got optical nerve cancer. It spreads to my brain. I'm fucked. But anyway, I've still got the brain at the moment. I don't want to talk about that, bro, because I'm not here for a fucking kid. Oh, sorry, bro. But yeah, we've got titanium, and there's another metal above that. It's basically an alloy, which is it's almost like mixed with platinum and steel, and it can go way higher. And we're on about using that as an exchanger from the reactor, which will then obviously we'll put high pressure water in there and create steam, and that'll turn a turbine, and that's how I think we're going to do it. But we can just never get there because we can't do it long enough.
So it was
6 seconds.
So 6 seconds for China. That was like the current world record. But how much? Like, what was the current record before that?
I think it was 2.6, if I remember rightly.
Wow.
You can Google it.
Wow, so that's a significant increase. That's a significant increase then.
Yeah, but the problem is, it's just like any engineer is just going to go, oh, shit, fucking, I'm not getting fucking fucked up for this. Boom, shut down.
Yeah.
So,
they're still running scared, basically. Like, they're tentative with this energy.
You've got 2 million Celsius in your reactor. If it breaks that magnetic confinement, the whole reactor is destroyed. So, as any employee, you're just going to go, all right, as an engineer, straight away, you're like, fuck this, boom, shut the cunt down.
Yeah, dude, I can see that. I can understand that for sure. Dude, that's tough, man. That's so tough. It looks so cool, though. I mean, this is amazing. It's really interesting.
That's 2 million degrees at the bottom of that reactor. So it started at the top on a big circle, and then what they do is the magnetic confine it right to the bottom, speed it up, because like a ballerina, when she brings in around, she spins faster. Yeah.
I mean, how much are we talking about? Like, how much material are we actually seeing? Like,
not a lot.
So, and then, wow. So, I mean, we're talking like a pencil head, like racer, head, or like a finger amount. Like what? I mean, what do you?
I have got a can of Coca-Cola here right now, which I'm drinking right now, and it will be less than that.
Dang.
But literally.
Wow.
Remember, E equals MC squared. So you've got energy equals the mass, which is, say, 330 millimeters of my kind of Coca-Cola, times C, which is C times C, which is 300,000 kilometers times 300,000 kilometers, and then I don't know the mass of a Coca-Cola off the top of my head, but I could calculate it. You could probably do it real quick. Work out the joules that would be created from that.
That's incredible, dude.
It's 300,000 times 300,000 times the moles, so it would go fucking off the scale.
That's wild. So and then how? So then the energy that is created and sustained from that amount, like how do they get energy out without putting more energy in? That's what I'm confused about. How would it indefinitely just create energy, or would it be just a small amount of energy that is needed?
There is no. It's perpetual. You don't need to put anything into it. It's going. The only issue, just real quick, just before you reply, the only issue is exchanging it to like some kind of usable energy source to get it to a pump.
Huh. Because it's
So
go ahead.
The goal is for that to never stop spinning, basically, right? That's the goal.
It does well. Just to clarify, it doesn't actually spin. It's a force, but yeah.
Right.
I guess it's just a way to just make you understand what's happening.
How, and then fusion is how these things are coming together. They're creating smaller parts, creating something bigger, right? That is what fusion is, right? And I guess how would they perpetually find smaller bits in order to make it into a bigger bit? Wouldn't it just there be more and more bigger bits that they can't combine, or how does that change over time?
Right. Okay. So fission, what it does is it splits the neutrons and the protons and the neutrons, and then it kind of splits and splits and splits and splits and keeps splitting. It creates loads of radiation, and you can use a different fusion reaction, and then fission reaction, and then you can also couple that. So the hydrogen B also uses fission and fusion, and it extended the kiloton rate to loads. All right, fair play for what they did there. But if you use fusion, so you're not splitting, you're putting them together.
Yeah.
So there's no radiation. It's completely clean. It is like the god, like energy source. Like there's no radiation. There's no nothing. Like Chernobyl. There was like people like unaliving, having to dump concrete on it, like to try and cover it up because like it was unalive in the world. And if it ever went wrong with fusion, nah. And I don't like using the nutter because that's flat earth thing. But yeah, it would just turn it off. There's no radiation. You could go straight into the reactor, fix it, sort it out, boom, back on.
Wow.
Like it's like a game changer.
That's cool.
It's just always 10 years away. That's the problem.
Yeah.
We can't keep it going long enough because like, can you imagine you've got 2 million degrees?
It's wild.
Popping out your.
It's wild. That's so cool.
Popping out of your nuclear power plant, and then the media. You got Fox News going, "Oh, boo, boo, boo! Oh yeah, look at this! It's popped." And we're like, "Oh fuck!" So the engineer just goes, "Boom, shut it down."
Yeah. What tritium is the byproduct? Someone Dave said in YouTube chat. Tritium. Interesting.
Yeah.
What was the thing that they're using? Platinum, you said?
No, well, they are using platinum, and there's another one called C something. I can't remember off the top of my head. Remember, I'm not very well. I've got cancer. But yeah, they're using other materials as well to deal with that. Carbon. Well, gallium, carbide, graphite.
Oh, dude, this is like some interesting. This is the part of the. As a biologist, this is the part of the periodic table that I don't normally go to. Thallium is down here, so it's very different. These are huge. These are gigantic.
Right, they're using carbon because the reason why they're using carbon is because what happens is it ablates. So I don't know if you know what ablation is.
No.
Ablation basically means when it gets too hot, it doesn't pop. Someone's at my door. What time is it? 7 a.m. Fuck off. Right. Okay. So carbon.
Yeah.
So do you know like on the Maverick film?
Yeah. Top Gun.
Yeah. Have you seen it at the first scene where he's going Mach 10 and you see all the sparks coming off it?
Mm-hmm.
He's like going, come on, one more bit, baby. Yeah. Yeah. Right. So that's why we're lining with carbon, because carbon it ablates because of the slate grain structure and of the material. It kind of burns off before it actually melts. It'll take off the first layer first, then take off the second layer, and then take off the third layer. It's very versatile.
Gotcha.
And that's why we use carbon.
That's cool. Cool. Well, Dave recommended How It Works ITER. How It Works ITER. Cool, man. Perfect.
It's called ITER, but yeah, whatever.
Okay, ITER. Thank you. I appreciate you. Yeah. Okay, cool. This is it. It's a 2-minute video. Perfect. All right, real quick. I want to finish this one. Let's finish this. This is like another 2 minutes here. Let's see if we can.
Hours, the teams worked under constant pressure. Every movement had to be perfect, and all of it rested in the hands of the crane operator.
Nous avons à peu près grand maximum 30 à 50
30 to 50 millimeters. Oh my gosh.
La charge en est en ouest, ce qui est très compliqué parce que chaque mouvement est calculé, anticipé et surtout, comme je le répète, c'est la sécurité.
And above all, safety is the priority. It's very complicated because these loads must not touch anything. So at the beginning we start in millimeters, so it's millimeter by millimeter. Then we move on to different speeds to reach 40,000, which is the standard.
When you speak, just turn the volume down a little bit because we can't hear when you speak. I am interested in the video, but just turn it down a little.
1,400 tons right at the fingertips may seem heavy. Oh wow, look at that. But with a lot of the professionalism and safety, we can do it.
That's Atlas.
Then we are surrounded by a team and the meteorology team who tell us what to do, especially with the engineers who give us the go-ahead and the coordinates. The meteorology team makes us stop to check the load that hasn't moved. We are all in contact with the bridge maintenance team Real, who are helping us with this challenge.
Yeah, that's Atlas. That. It measures things in nanoseconds.
Dang, that's amazing.
Picoseconds, I think. Is it pico? I think it's pico.
Yeah, bigger than that. Yeah.
A mirror, which they will reflect the signal of the tracker and the total station. Based on the readings, we will know the actual position of the sector. After, we know as well our reference, which is the pit. So we will know the relationship between the pit and the sector, and based on that we will be able to guide the mechanical team to make the sector match the.
Dude, that's wild, dude. Because because if they misalign it, then the magnets will be all messed up, and then the whole thing is screwed.
No, there is protons flying through the center of that at near the speed of light.
That's crazy.
And look how much weight. That is only one detector. There is two. Okay. We're now drilling and making 100-kilometer radius CERN.
Wow. Dang, that's incredible. It's giant.
A mechanical position that we aim for.
By 5 o'clock the next morning, Sector Module 5 was nearly in its final position.
It's the achievement of a teamwork and team with the lifting teams from SMSA, the contractor, IO, construction teams, assembly teams. The teams that I supervised for the crane operation and the crane maintenance. It is like a new baby in the nest.
Dude, that's crazy.
See how much this cost us? It cost us billions.
Yeah, it's like 10 billion euros.
Upgrade it again.
Yeah.
It's cost us billions, and now we're doing 100-kilometer. We've got TBMs drilling underneath the Alps, right? That's going to cost us another 15 billion. And so we found the Higgs boson. Okay, that was the first step. Okay, yes, we know it interacts with gravity. Okay, so we found the God particle. Okay, next thing, we need to find the graviton. But unfortunately, we've already done what we can, and it can't be upgraded anymore. We need to upgrade, and that's the only way. Drill, baby, drill.
Yeah, make it bigger, huh?
But it's like that. It's like I know I was pivoting away towards astronomy, but I mean, look at that plasma.
That's crazy. Hey, Michael from YouTube chat, the reactors are lined with materials like tungsten, beryllium, and carbon for the inner walls, and steel, vanadium alloys, and ceramics for the structural components. Dang, dude. That's stuff that I do not... I only know my materials from World of Warcraft armor. So if it's stronger than steel, I'm out. Beryllium, I don't know if that even is. That's that's incredible. That's cool, dude. No, I mean,
yeah, but you can imagine that plasma is 2 million degrees.
That's wild, man.
Celsius.
That's so cool. No, I mean, we have to fund stuff like this. This is important. This is stuff that we can change the world with. I mean, we have to be trying to improve problems, right? I mean, there has to be some investment into the future.
I think the whole goal of investing in infrastructure is for it to work as efficiently as possible. Basically, you want to lessen the need of heavy maintenance in the future, right?
Yeah.
Because if you build it right the first time, and you make it, as perfect as possible, it should pay for itself many times over.
Yeah.
Down the line.
Okay. Yeah, I'm gonna back you here, Eric. Is it? Sorry, mate. I've got optical nerve cancer, bro. My eyes aren't very good. Is it, Eric?
It is.
Yeah. Yes, it is.
Right, okay. So with this, there is no moving part. There is nothing. It just, I'm going to use Todd Howard with his Sky thing. It just works. But this thing, there is no moving part. When it's going and we manage to work it out, and we can't, we get our magnetic confinement sorted out, we're done. That is it. Game change. absolutely game change.
Mm-hmm. Yeah, for sure. So here's the how it works video on how this stuff. All right, we're gonna watch this real quick.
ITER, the biggest science collaboration in history, aims to prove that carbon-free fusion energy can be produced on an industrial scale. It will do this by creating and controlling a miniature sun inside a device called a tokamak. The tokamak will rely on 3 unique, powerful electromagnets to spark and control a plasma, or ionized gas. At the very center is a 5-story, 1,000-ton superconducting magnet known as the central solenoid, or the heart of ITER. Its chief job is to induce and maintain a powerful electric current in the plasma that will result in energy-producing fusion reactions. This happens through a carefully orchestrated sequence of steps. First, electric current is fed through the outer coils to create magnetic fields that will help shape the plasma. Next, a current fed through the central solenoid is gradually increased over several minutes to 40 kiloamps. As the current increases, it creates a growing magnetic field. Next, it's time to add the fuel. A few grams.
What was that? Dude, it's crazy how quickly it happens.
1,000 amps.
That's
40 kiloamp.
That's crazy.
Keep going.
That's wild, man.
Of deuterium and tritium gas. When that gas is heated up by a strong pulse of microwaves, it breaks down into charged particles to become a plasma. Just like a wire, lightning, or other conductor, plasma can carry a current. Now is the central solenoid's big moment. A lot happens, quickly and simultaneously. But here we'll show one thing at a time. First, tokamak operators rapidly reduce the central solenoid current. That causes a sudden change in the solenoid's magnetic field, which in turn induces a current in the plasma via electromagnetic force. Transformers transfer electrical energy between circuits the exact same way in power lines. Operators maintain the plasma current by continuously changing the solenoid current and its magnetic field. More slowly now, for several minutes. More heat is added to the plasma until deuterium and tritium ions have enough energy to collide and form helium, a reaction that releases huge amounts of energy. By demonstrating that we can use fusion to generate abundant power, ITER will help pave the way for the carbon-free fusion power plant.
That's cool, man. That's way cool.
Of tomorrow.
That's awesome. That is so cool.
Yeah, it's just not. We're just not there yet.
And
then
2033. I mean, the 2033 for ITER. So that's cool.
Yeah, but then when we are there yet, then it's going to fall to me as an engineer and go. So some random physicist in the office will roll up into my office and go, "Oh, by the way, you need to make an exchanger for this fucking reactor, and you need to make some turbines for this, and oh, by the way, it's going to be 1,500 psi steam." And I'm like, well, you fucking wanker.
Exactly. All right. Well, guys, thank you so much. I really appreciate you coming up. That was awesome. I did not expect to deep dive fusion reactions tonight, but that was really fun, and I appreciate you coming up. Thanks, Jerome, for coming up with your expertise, man. Thanks for Eric for being here, asking some awesome questions.
I'll drop her again, bro. Have a good night. It's really early in the morning for me.
Thank you, man.
Get some sleep.
Yeah, brother.
Multiple lights.
All right.
I'll send you a few likes and a few guests.
Thank you, brother. I appreciate you, man. All right. See you guys. Dude, awesome, guys. Thank you guys so much for coming on. I really appreciate you. Did not expect to go over that. That is amazing. Thank you, guys. Thank you to our guests, Eric and Jerome. Thank you, guys. Appreciate you. Appreciate you, Jerome. Appreciate you, man.